Let's see another example. Here we are given that in the system shown in figure block A is pulled toward left at a speed v1. And we are required to find the velocity of block B when string makes an angle theta with the horizontal. Now as block A is moving toward left with v1, we consider its displacement say from reference point which is vertically below B. Say this point is O. Let us consider this distance is x. So we can directly write this v1 is equal to dx by dt. And if the length of string we consider to be constant, and it is say L, and the distance of block B from the topmost point of string is y, we can write this distance as L minus y. And here, as block B is going up say with velocity vb, y will be decreasing, so I can write vb equals minus of dy by dt. Now I must try to relate x and y. If the total distance above the ground the pulley exists is say h, this will always remain constant. So, very first thing I relate is relation in x and y. This can be written as x square plus h square equals L minus y whole square. You just have a look at the two constants I have introduced in solution. One is the length of string, other is the height of pulley above the ground, that is h. I can introduce any number of constant because I know that I'm going to differentiate this expression, and free constant will certainly become 0 on differentiation. Here if I differentiate it with respect to time, you can see x square will become 2x into dx by dt. H square differentiation becomes 0. On this side it will become twice of L minus y into minus dy by dt. This 2 gets cancelled out, and you can see that dx by dt I can write as v1, and minus dy by dt I can write as vb, so here it becomes x into v1 equals L minus y into vb. We are required to find the value of vb, so here you can see the value of vb is equal to this x upon L minus y multiplied by v1. Now in this expression x upon L minus y we can calculate by using this triangle. Here you can say x upon L minus y can be written as cos theta. So this will become v1 cos theta. So we are required to find the velocity with which block B is moving, that is v1 cos theta. This is our answer. But other than this analysis we can also evaluate this result directly. As in previous examples we have studied that we can also equate the velocity components along the length of the string. As the string length remains constant, we can simply write in alternative method over here only. As block B is going up with a velocity vb, the velocity of string along its length will be vb. On the other side as block is going toward left with v1, along the length of string the velocity of string will be v1 cos theta, and as the length of string is constant the two velocities with which this end and the other end is moving along the length of the string must be constant. So vb can be written as v1 cos theta. This is the direct way to approach the result, and this mathematical analysis of constrained motion by which we have evaluated the result. Both the method you must know, because in majority of cases this is useful. But in such cases, when string are connected with block, or you can say one or more strings are there, or blocks are in motion, so we can also relate the concept of string length constant with the motion of blocks like this.